So good evening, everyone. A very warm welcome to every single one of you. Thank you so much for joining in. Promises to be a very, very interesting session. It is a technical session, but I would like to vouch for the quality of the content and the focus that our esteemed speaker from Little Fuse will be putting in to make sure that he will deliver a very, very content-rich session. And please feel free to add your questions onto the Zoom chat, and later on we can also interact with him. So without further ado, I would love to also get everyone's okay that we're ready to start. You can just put a thumbs up and put a yes on the chat. Fantastic. And now I would like to get Vivek Sharma, who's our expert speaker today, to please start the session. Thank you so much, Vivek, for taking the time out and preparing what I know is going to be a really wonderful, knowledge-driven seminar, workshop, conference, webinar, whatever we want to call it. So over to you, Vivek. We thank you for your time, and also shout out to Mauser Electronics and the IoT Forum, who have always helped us and have been with us to bring together such kind of very, very high quality sessions. So Vivek, over to you, and all of us are looking forward to this session. Thank you so much.
Hey, good evening, Vijeta. Thank you for having me, and once again, very warm welcome to everyone of you who has joined. So today we are going to discuss general port protections and the protection schemes that one can deploy to prevent most common type of failures therein. So first of all, a brief agenda. We'll start with the introduction of communication ports that we shall be covering today. Obviously, not all the available ports in electronics are being covered, but the principles that we shall discuss can be applied to other communication ports as well. Then we'll be covering like what are we protecting these ports from? So what are the threats? Now let's admit, as an engineer, we are interested in specific issues that we need to pass. So what are those magic numbers? This question would also lead us to governing standards. Next, some of the commonly available protection components will be discussed. And then finally, we'll start the real journey of covering power ports first, followed by USB Type-C and traditional USB 2.0, HDMI, DisplayPort, so on and so forth. And lastly, we'll have like, low-speed ports. So now, as one can see, this is quite a bit of work. So let's get started without any further ado. Okay, so what's a port? Textbook definition is that it is a pair of terminal connecting an electrical network or a circuit to an external circuit as a point of entry or exit for the electrical energy. The ports can broadly be categorized into power ports and communication ports. Now, power ports, as the name suggests, are the ports used for transferring power from one circuit to another. Okay? And communication ports are all about data, low speed or high speed, but yeah, they are all about data. So why can't we have common protection for all the available ports, or one type of protection for say power ports and like one common protection for all the communication ports? Well, it turns out that each type of port has different requirements and is made up differently. So take the capacitance requirement, for example. This slide shows number of communication ports from low-speed MIDI to all the way up to DisplayPort and USB 4.0, which are really, really high speed. Right? So typically, capacitance requirement of the device used for such protection is inversely proportional to the data rate on that particular channel. So faster a device, lower the capacitance you will need to have of the protecting element. Now, similarly, power and surge expected at these ports would differ depending on the application and installation. So this is the reason we cannot have one common type of protection for power or communication ports. Okay. Now, research shows that 75% of all field equipment failures is due to electrical overstress. That's huge, right? 75% and this is caused by transients. Now, this slide shows different kind of surges which can affect the system. Now, power, cross, and short circuits mentioned on number 4 and number 6 here. Right? They're self-explanatory. I'll not go into depth about all this, and are typically taken care by introducing an overcurrent protection device such as fuse or PPTC, resettable PTC. Now, selection of fuse or PPTC is a detailed topic, something I don't intend to cover today, but then you can find valuable information at Fuse website for this. Let's take some time to understand other transients better. So this slide shows different kind of transients with severity level of the voltage plotted against their frequency of occurrence. So on top of the chart on the left hand side, we have as direct lightning strike. Now this happens when lightning from the cloud directly falls on the equipment very close to equipment. So this is typically very high energy pulse. Now it has a typical voltage of hundreds of kilovolts and almost impossible to contain at equipment level. Luckily, however, this is quite rare, and hence this is something we don't need to worry much about. Okay. Secondly, what is most frequent is indeed induced lightning surge. Due to large current flow in the event of direct lightning strike that we just discussed, there is a huge amount of discharge of electrical current. Now, this discharge of electrical current leads to creation and spread of electromagnetic field in the surrounding area, of course. The energy thus created is carried to above the ground and below the ground cable, and which ultimately is discharged through various equipments connected to these cables, and hence causing failures in these power cords. Another kind of surge event is switching surge that occurs due to switching on and off of inductive load. Here, power is not that high as an induced voltage surge, but its frequency is much higher. As one can see that at any given point on any equipment, there would be like 10 other loads connected around it. So any switching on and off of those would also impact it. So that's why we need to cover like switching surge. Next in the line is ESD. Now ESD stands for electrostatic discharge. The buildup of static electricity can be caused by a phenomena called turbocharging or electrostatic induction. The ESD occurs when differently charged objects are brought together or when dielectric between them breaks down. Now, time duration of ESD event is quite small, typically less than 100 nanoseconds. And it is a low energy event. However, it is a very high voltage event, which can create problem to the equipment and hence requiring expensive repairs. Now, other two kind of surges mentioned here, like pulse noise, which is taken care of using filters. And then we have got one very application specific thing mentioned here, low dump surge. So I don't intend to cover low dump surge, but we do have solutions for this. But as it is very much application specific, so maybe that's a topic for another webinar for some another day. Okay. So to protect from different kind of surges, we need to simulate these, and that's where standards help. Each of these standards have processes and methodologies clearly defined for simulating these events. For ESD, most common standard for end user equipment or end equipment is IEC 61000-4-2. Now there are some others like HBM or human body model and CDM or charge device model, but those are more of a component level standards. HBM or CDMs were developed actually for simulating ESD on the production line of electronic devices, ICs, so to say. Okay. So that ICs would be functional while they are being shipped out, and they don't get killed even on the production line. That's why they were developed. So what these don't simulate is the real world ESD that your final equipment may experience in the field. Now IC standard is more severe, and that's what we are discussing here. So test levels defined in IEC 61000-4-2 vary from 2 kV to 8 kV. But this standard also allows for X level, so that manufacturer can test their equipment for the levels well above 8 kV. Now IEC 61000-4-2 is the best, or I would say like most common standard, but not the most severe standard. There are other standards like ISO 10605 interior and exterior, that simulate ESD environment inside and outside the automobile, and have max test voltage of up to 25 kV in the case of exterior standard. Now, ESD is quite a small event, right? With the rise time of less than 1 nanosecond and duration of little above 100 nanosecond. So, for EFT or electrical fast transient, which simulate like inductive switching or contactor switching, most common standard is IEC 61000-4-4. The test waveform has a rise time of 5 nanoseconds over a period of 50 nanoseconds. However, it occurs rapidly over a period of 15 milliseconds, so energy buildup is significant. The pulse loop is repeated after an interval of 300 milliseconds. Voltage standard for this particular test can be up to 4 kV and current up to 80 ampere. Finally, we have lightning events. There are a couple of standards to simulate lightning. Among these, IEEE C62 is the basic one from which other standards do borrow for formulating the processes for their intended end applications. For example, if you talk about UL 1449, it's a surge protection device lightning standard. Now, internationally, IEC 61000-4-5 is the most popular standard for lightning. The voltage level in the standard go from 1 kV to 20 kV and current level from 500 ampere to 10 kiloampere. Now, waveform that is used to describe these surges is called combination wave, which consists of an open circuit voltage waveform and short circuit current waveform. Now, there are some figures attached to it actually. So open circuit voltage waveform has a rise time of 1.2 microseconds and fall time of 50 microseconds. And short circuit current waveform has a rise time of 8 microseconds and fall time of 20 microseconds. The waveform is quite popular in power distribution, so I'm sure many of you would have heard about it or actually worked with this as well. In other fields such as telecom, you might come across like 10 cross 1000 or 10 cross 700, but essentially what all of them mean is rise and fall time of the waveform, which is actually used to depict the energy associated with the surge. So, what technologies are available to deal with these transients? There are two types of basic devices for dealing with the surges just mentioned. A clamping device and a crowbar device. So what are the clamping devices? Clamping devices adjust their resistance value as per the voltage applied. So during the transient event, it will start to conduct once a particular voltage is reached, thereby maintaining the voltage by allowing extra current through it while the surge condition lasts. Now, this maintained voltage is higher than typical operating voltage of the system, but lower than the damage threshold. For example, in this case, if this is the operating voltage, then that's where it lands. So damage threshold of the equipment should be somewhere here, above it. After the transient, the clamping device typically restores back to its high resistance state, as you can see here, and hence allowing for normal operation of the circuit. So examples of the clamping devices are mentioned here, MOVs and TVS, metal oxide resistors and TVS diodes. Okay, now what are the crowbar devices? Now, in crowbar devices, once a trigger voltage is used, it reduces its resistance down to zero or very much close to zero. After the dissipation of the surge, the device delatches and goes back into its high resistance state. Now, we must note that here it is necessary for a current through crowbar device to fall down below a level after the dissipation of surge. Otherwise, current would continue to pass through this and device would fail. I'm talking about this point. So once surge has gone, your current should somehow reduce. But typically, nothing happens automatically unless you don't have have something to force it. So this is the reason you do not see crowbar devices being used on their own for managing those surges. And typically, you will see them being used along with the clamping devices. Okay. However, there are some exceptions to this rule as well. I mean, we'll see further down in the slides that a crowbar device may be used in some cases for protection. Now, example of crowbar devices are gas discharge tube and SetE. Please note that explanation for operation of this component has been slightly oversimplified for brevity of time, of course. And there are typical substages during their operations, but I hope you get the idea. So how do these devices compare? So a couple of observations to be made. First, that the breakdown of the devices, voltage at which the resistance of these devices begins to come down is not constant, but it is also dependent on rate of rise of voltage. As can be seen from the graph on the left-hand side, this one, the effect is more pronounced in GDT. This reveals that GDT are slowest of the lot. Right? So while using them, it becomes important to be aware of this shortcoming. Second takeaway from this slide really is that graph. You just look at the graph on the right-hand side. There is a so once you have got clamping voltage or even with the crowbar devices, there is a terminology named let-through voltages or clamping voltages. Now, clamping voltages are not equal. For a typical application, you will see that TVS diode allows you the lowest clamping voltage and GDT gives you the highest. So this is the voltage that appears across your protected equipment. That's the second point. Third is that surge handling capability. It's high for both MOVs and GDT, but not so much for TVS. Again, there are some exceptions to this rule that something we'll see in the remaining part of the webinar. Now, leakage current is not much of a concern in either of these three if selected properly. One very important thing to observe here is pulse cycle capability. The pulse cycle capability means the ability of a component to successfully take a given surge repeatedly. Now, TVS diodes are particularly great in this respect because given that the repetition rate is below the specification, TVS diodes do retain their capability to bear the surge, unlike the MOVs or GGTs. MOVs and GGTs do degrade with each and every surge. Okay. That's why you'll see that pulse cycle capability of TVS diode has been mentioned as excellent. Okay. Finally, one thing I wanted to observe is on capacitance. So GJT is best in this class. They are the lowest capacitance, but just because they are slow, you won't see them being used as much for high-speed signaling. Now, with this primer on surges and devices, let's start with the protection scheme for various ports. And first in the line is power port. Okay. So first place for a lightning consideration is usually power port. And this logical because electrical cables that travel for miles are known carriers of induced voltages. Depending on the position of installation, the such specification may vary, but idea remains the same. We'll discuss both AC and DC ports. So this is the AC port that we can discuss right away. Now this slide shows AC power port system that uses MOV in differential mode for lightning surge protection and fuse for overcurrent protection. Now, any surge from upstream power system is taken by MOV and let through voltage or the clamping voltage appears on the downstream power module. Now, proper selection of the voltage or the power rating of this MOV must be done in order to ensure that this is able to sustain that surge from upstream, and also that the clamping voltage is below the maximum sustainable voltage by this power module. Okay. Now, this all looks too simplistic. However, it is worth noting that in some cases, like we all know that MOVs do have limited pulse cycle life, right? So once it has run its life, the circuit would keep operating even without protection. Now, this is not acceptable in some situations. For such applications, we would like to propose our TMOV family, thermal MOV family. So it has a part with the 3 lead. The middle lead comes after the thermal fuse. Now this lead could be used to learn about health of the MOV, and you can give an enunciation or indication of LED, for servicing the product or stop its functioning altogether, depending on your requirement. So that was just generic description about AC circuit. Now, however, if you want to have a look at the complete system, such as say LED installation, you might see something like this. Here, first in line, you'll have SPD block, and then you'll have onboard protection, what you have in for the surges in driver. So SPD would take bulk of the surge, and remaining surge is taken care of by the input driver section. Now, it is important to select voltage such that design would sustain maximum expected voltage for required number of hours. Now, MOV in SPD being in parallel with MOV with the driver section, these two, you just have a look at them. Like this is in parallel with this. So it is important to choose a voltage so that proper coordination is there. Like ideally, we would want more than 95% surge to go into this MOV. So voltage rating of this should be lower than this. Another point that I'm asked many times is that why don't we have extra ESD suppressor at power ports, even though they are exposed to the user? Answer to this is because already they have a protective element, like MOVs or TVS though rarely, is big enough to take care of those small transients. We saw that ESD is quite small. Okay. Now, protecting DC circuit is relatively simple because they don't have much risk of induced voltages. Hence, depending on your requirement, you can have a TVS in SMC or SMD package, or even small MOV can be used. And that's what we are showing here, small TVS. And however, in some applications such as telecom or high security surveillance, where downtime is not at all acceptable, we do see customers using high power TVS from little fuse. Now the one being mentioned here, like from AK family, it can sink as much as 20 kiloampere of the surge current. So you remember I talked that they do not have high power devices. That's generally true, but yeah, there are some exceptions because there are some specialized devices for that. Now, one caveat for while using MOV in parallel with the TVS diode is that typically in this case you will see an inductor being used, so as to provide the proper coordination. Now, inductor used here should have high inductive value and actually should be air core, because if you try to make it in iron core, then that would tend to saturate and that would be counterproductive. Similarly, moving on to DC input and like PFC circuit. So because PFC would already boost the voltage, you need a higher voltage fuse, and then one MOV could be sufficient here. For portable devices like DC imports, it's not much of a concern. Only thing is that typically portable devices should would be using a PPTC. These are resettable fuses. So current goes beyond a time, it just provides a very high resistance. And once you remove and reset the once you remove the fault and reset the device, you'll have the device working normally. Okay. For DC output also, unless you are expecting some inductive kickbacks, SMBJ would be sufficient. If there are some inductive kickbacks on your circuit, then probably SMCJ or SMBJ would be a better choice. Now let's move on to high-speed circuits or high-speed interfaces. There are many high-speed interfaces, but one which is getting most tractions for these days is USB, and mainly USB 3.2 and these days USB 4.0 actually. And both of them implemented Type-C. Popularity of USB Type-C can be attributed to the fact that this can not only send high-speed data signal but can also provide power using sophisticated signaling for host and slave selection. Now, this is the reason you see so many devices in the market right away, from like phone, laptop, tablets, gaming consoles, wash machine, you name it, using USB-C. So what are the challenges in implementing USB-C? First, the connector in USB-C is smaller and reversible. Second, power has increased manifold. Third, there are some really crazy high-speed signals there. These are actually known as lanes, high-speed lanes. So in 3.1 generation 2, it's 10 Gbps, but in 4.2 generation, in USB 4, it goes all the way up to 40 Gbps. And similarly, in Thunderbolt also, you have a speed support of up to 40 Gbps. So what is the challenge if the speed is so high? So whenever you're trying to maintain, you're trying to provide ESD protection, you also need to maintain signal integrity. And hence you need parts with lower capacitance. It should not distort even these signals. Okay. And how does having smaller connector create problem for us? First is that it leads to tighter pin spacing. So any small debris, say, any conductor debris going there can introduce heating faults. And then we have already quadrupled, or maybe actually 6 times, the power has been increased. So with great power comes the great thermal risk, probably. So here's a summary of what has happened. Like, the size is smaller even than USB micro B type 4. Okay, even with respect to this, the USB-C is smaller, and then in the power delivery mode, power can go up to 100 watts. So that increases overall thermal risk. Now let's see how a USB Type C system is implemented. Now, there are two basic structures which are slightly different. The receptacle that goes into the device, like phone, and the plug that goes into the end of the cable. Right? As we clearly mentioned here. Now, there is a new line, called CC or communication channel. The receptacle has two pins for CC and plug has one, marked here in red. You see, receptacle has two, CC1 and CC2, while plug has got only one. Okay. Now, since plug has got only one, it is used to determine plug orientation or which way did the cable get plugged into device's receptacle. The CC line is also used to determine when a complete circuit of source, cable, and sink are connected. Once a connection is detected, the source and sink use the CC line to agree or handshake the power level on power level and data speed. To detect the cable, a voltage measurement is done on CC line. Now, if voltage is higher than a specified value, it is assumed that no voltage is attached. Right? So this is all new. The CC line concept is new to Type C. If there is no source to sink connection, as detected by the overall implementation, then the VBus is kept at 0 volt. So no voltage is applied on the receptacle side. Okay. So standard implementation of USB-C system uses 24-pin connector. Though it is not uncommon to find 16 pins and 6-pin implementations of specific applications, such as chargers, etc. These are coming up mushroom these days. Now, 6-pin connector would, for example, contain only VBus, CC, and ground. Now, pins are duplicated on both the sides so that orientation of the connector would not matter, and that's what makes it reversible, right? So please note, pins are not only duplicated, they are also transposed, right, from left side to right side, because when it would be flipped, this end would come on the top left. Okay, so how do we protect USB-C? Speaking of overcurrent protection, first protection that comes to our mind is resettable PTC. However, here wattage is quite high, hence that would lead to system inefficiencies. So Littlefuse came up with an innovative solution for this, and the solution is called SetP. Now, so suppose there some external fault happens due to debris or improper connector connection. A short happens between the VBus and ground. Now this would lead to very high flow of current. This current in turn would create heat on the connector subsystem. Now SetP uses this heat and increases its resistance to very high value. Note here, a couple of ohms to very high value. Okay, and this in turn makes the overall subsystem to feel that there is no charger connector or downstream cable is not connected, and hence the voltage on VBus is reduced to 0. And that's how your overall cable and subsystem is protected. So where do we install this SetP? SetP is installed typically at these points on the cable plugs. We do have suggestions for other, transient protections and other things from Littlefuse portfolio, but right now I'll restrict my talk to USB, USB Type C. Similarly, for captive power cable, we'll introduce SetP here. Now, what are the benefits? It's a small size, it's sensitive to the temperature, 100 degrees, and it's really rigid, and it's independent of power because it doesn't care. All it needs is the high temperature. Has been tested for like 20,000 trip cycles. Okay, so how does overall protection look like? So SetP in series is okay. And this is something we have already explained. Now USB 2 signals, because USB 3 and 4 are backward compatible with USB 2. So USB 2 signals and V bus are also there, and they don't need any low resistance part. So we will try to have one part with a low R dynamic and low clamping voltage. V bus can go as high as 20 volt, right? So we'll need a part with a standoff voltage of 20 volts. So we have suggested a part with a reverse standoff voltage of 24 volt. Now, super speed pins need parts with low parasitic capacitance. Nothing so special about SB pins though, except that they are required to be in the small footprint. Now, if you're using USB Type A and Type B, then on power line, we'll suggest some PPTCs. And for others, you can have a look at these protections. I'll just move on to the next slides. But these are special protection if you take care of 3.2. But for USB 2.0, it's very generic because you need a data speed itself is not very high, only 480 Mbps. Okay. For HDMI and display port protection, we would suggest a 4-channel diode array. So a full HDMI port implementation may require one to use like 3 of these chips, while an external SATA, you might be good with just one. Now, I must insist that for these applications, the user must have a look at transmission line pulsing diagram of the selected part. This should give them good indication of how the part is going to behave in case of ESQs. Lastly, it's important to test these suggestions. Now, let's move to next port, which is Ethernet. Now, I'm sure everyone has seen Ethernet connectors. There are basically two types of connectors approved by TIA, Telecom Industry Association, with T568B being the most common. Each one has 4 pair of wires. Difference is in the relative position of yellow and green, if you look carefully. Now, there are 4 kind of implementation of Ethernet from speed standpoint: 10 Mbps, 100 Mbps, 1 Gbps, and 10 Gbps. From protection angle, I want you to note that 10 Mbps and 100 Mbps use 2 pairs of wires, whereas 1 Gbps and 10 Gbps use all 4 pairs. Something is mentioned here. Right? So higher speed use all 4 pairs. There are some other differences like simplex versus full duplex, transmission, encoding, signaling, etc. But that's besides the point. Okay. So circuit protection, how do we protect Ethernet solution? Now, Ethernet could be implemented intra-building or inter-building. Intra-building is the most benign atmosphere that you'll get for Ethernet. With very limited scope for lightning, these solutions typically require very little protection. So basically what we recommend here is a diode array such as SRV05. The device can tolerate up to 20 kV contact and 30 kV air discharge. If you move however to outdoors, the situation becomes much more critical. While designing for the harsh environments, there are multiple telecom standards depending on your project requirement that you might have to follow. One such standard that comes to my mind is GR1089. In addition to other requirements like overvoltage and ESD, this guideline GR1089 calls for protection in case of power cross. This is done because Ethernet and power cables run very close to each other. The combination of 0461 fuse that we have suggested here along with the GDT provides a compliant solution for the standard and recommendations such as GR1089. GDT mentioned here works to absorb bulk of the lightning surge on the primary side. Okay. Now, the particular case in point is of Ethernet implementation is PoE, the power over Ethernet, which is a powering technique used over the Ethernet wiring link. Now, there are 2 advantages of PoE. First is that Ethernet devices are not required to be placed to wall outlets. So no unnecessary outlets would have to be created. And second is power cables are no longer required to be created. Now, examples of PoE, there are many. If you look carefully, like CCTV installation, biometric, access control, signage, VoIP, etc. Okay. So let's try to have basic understanding of how PoE works. In PoE terminology, the device that receives power is called powered device. And device that supplies the power is called power source equipment, PSE, PD and PSE. The source take, the standard, whatever you're concerned with here, IEEE 802.3, it takes care of losses during power conversion and transfer. So as you can see in PoE, PSE can supply up to maximum of 15.4 watt, but PD in this particular case can accept maximum of 12.95 watts. We have similar standard for PoE++ and PoE++ type 3 and type 4 as well. Now, one thing that has to be kept in mind is the kind of stringent policies or directives this standard gives you as you move from PoE to PoE+ and PoE++. Because now the cable should be of very low impedance, less than 12.5 ohm per loop pair, such as Cat 5G or Cat 6. Okay. Now, to be compliant with IEEE 802.3, an Ethernet port must comply with following electrical isolation. So you can have a look at it. I'm not going to read it out for sake of time. So these are the isolation tests. One of these has to be passed. Pricing criteria is that no isolation breakdown during the test, and resistance after the test shall be at least 2 megaohm when measured at 500 DC. Now, power in PoE can be inserted either in endpoint PSC or midspan PSC. This prevents having to rework the entire network. Now, there are two basic modes of power insertion in PoE. The power can be provided in one of two ways, like over the same pair as data signal, or over the unused pair in case of 10 Mbps and 100 Mbps. Remember, there is no unused pair in case of 1 Gbps and 10 Gbps. In mode A, power is applied over active pair in case of 10 and 100 Mbps. Like just note these designations 1, 2, 3, 6. 1, 2, 3, 6. So in mode A, the power is supplied over them. Right? So PoE uses a phantom powering technique, so that a single pair comes to 0 DC voltage potential difference. Two center tap connection provide access to DC power, and DC voltage across any single pair remains 0, as you can see here. Right? The power is from positive side, it's given to the one set of pairs, and on negative side, it's given to the another pair. In mode B, power is applied over the unused pair in case of 10 base T and 100 base T. So these connections make 4, 5, 7. Okay. Please note, it's the PSC that defines the mode type. Therefore, it provides power in a single mode only. It cannot provide power in like both mode A and mode B. I hope that's clear. Okay. So how can we provide protection to such a port? So what we are suggesting here is that you use our product known as side actors on primary side, and then you can have some ESD components on the secondary side. The main thing to note here is that ground on primary side is different than ground on secondary side. Typically, these are connected using a say a 2000 volt ESD capacitor, say of 1000 picofarad or something of that value. Okay, then we can use on DC power sinking side, we can use a TVS diode. Now, standoff voltage of this part should be greater than maximum voltage. Nominal voltage on PoE is 48 volt. So maximum voltage here is 57 volt. So we are suggesting here a part with 58 volt. Similarly, you can use one before the DC-DC controller and again one previous time. So these are some features and salient benefits of the component suggested. You can read them. So another popular interface for industrial space is RS485. So how do we protect these ports? I mean, we can suggest a PPTC here and a ESD component if it's intra-building. Because intra-building, as I told you earlier, in the case of Ethernet, it's very benign. If it goes to outdoor, then of course we'll still be using PPTCs and gas discharge tube and side actors. However, we'll have to, here the PPTC acts as proper coordinating element so that these fire at exactly the right time to give you the required protection. Okay. Lastly, let's have a look at some low-speed interfaces. Now, I have taken this example of RS232. I'm sure each one of us who has worked on in electronics has seen or worked on RS232. This used to be so popular back in the day. Okay. So I have used this to illustrate one very important concept. If signal on a line that we are trying to protect is unipolar, then unidirectional protections can work. But if the signal can traverse both the sides of zero, then we need a bipolar protection. However, reverse may not be true always. Like unipolar signal lines may be protected using bipolar TVS for protection. This is typically done in the high speed lines because bipolar ESD protections have lower capacitance, which is not difficult to understand, right? Because what you will get is back-to-back capacitors. So this example here, you see a bidirectional implementation of SM15, which actually is a unidirectional part. You're using two of them, attached back-to-back. Okay, for CAN and LIN, we have parts, multiple parts. The part is listed here as an automotive qualified part, but we do have parts to take care of, the ESDs in, different parts to take care of ESDs in such scenario. In case of SIM or micro SIM socket, we have a single part that can protect, because here we are not talking about extra low capacitance part. So we have a part that can protect, a single device can protect the complete module. Okay. Then antennas and sensors. Now antennas typically work on very high frequency. So as one can understand, they need parts with the very low capacitance, but they also are susceptible to ESD. And because of the way they are placed, they are always open to environment, and anyone can touch their human body being one of the great sources of ESD. So this makes a case for our polymer ESD suppressors. Now this part has a capacitance of 0.09, so less than 0.1 picofarad, and can withstand ESD up to 30 kV. Now sensors do not warrant a part with a very low capacitance, but what they need instead is a part that should act very, very fast. So we are suggesting a part from our silicon array line. So this is about now about audio and video lines. Now audio lines can be protected using SP1002. This is the part that we are suggesting here. The part has a capacitance of 5 picofarad and a low leakage current, but this may not be sufficient for video line because here the capacitance required will be lower. So we are suggesting some different part here, SP3019. Now keypads, they don't have any capacitive requirement, so we need even a varistor MLV part can be used here. This part is listed here as the automotive qualified part. And similarly on the battery packs, we have a huge portfolio to support our customers. But here I'm just concerned about the ports, so we are suggesting a fuse and a ESD part to take care of ESD surges. So that's it from my side. Here are a couple of design guides if you want to take note out. Probably you can download it from the resource section. And with this, I would like to hand it over back to you, Vijeta. Hello.
Yeah, thank you, Vivek. Thank you so much. Now I'm just getting Avinash also and Vinay also from our team into the picture because we have a few questions that are there for you all as well, Vivek.
Yeah,
There's
I
a
think.
question. Yeah, if you see, there are 3 questions that are there from Manish and others. But I would
Okay.
request this interaction to be had along with the mouse electronics person, Avinash. Avinash, over to you, sir. Thank you.
Hello, everyone. So Vivek, thanks for this session. And also about mouse electronics, we would like to say that mouse electronics is one of the leading distributor with respect to the electronic and semiconductor products. You can visit our mouse electronic website and you can see the list of the products what we have. And Little Fuse is one of our key distributor. So Vivek, we have a question from our audience. Okay. So the first question, is there any standard formula or a standard rule available to decide the protection circuit component value based on the input voltage? So that was the first question from Srikanth.
Okay, based on the input voltage.
Yes.
So we did briefly discuss, but probably not in that detail. So one thing that I would like to mention here is first that your reverse standoff voltage of protection component. If it is a parallel component such as the crowbar and clamping device that we suggested, its reverse standoff should be more than the voltage, maximum of the voltage available. Okay.
Okay.
So that's one thing that you need
So Srikanth, I think you have got your answer for the particular question. I think if you require more details, you can just drop a mail to Vivek. Vivek, maybe you can just drop your email on the chat box. So next question we have from Prithviraj. Do current EVs also have issues with respect to load dumps, or is it only in the ICE vehicle?
See, load dump is a spec that typically is there only for the IC engine, because you have to see how you get load dump. It's as in a scenario where your alternator is still supplying power to the battery, and your battery gets disconnected. The kind of shock that your overall electronic system gets, that's the load dump, right? But in case of EV, you don't charge it while running, right? So it's only charged when it's parked. So though there are some other surges to take care of, but not load dump per se. Sorry, I can't hear you. Sorry, I can't hear you.
So Prithvi, I think you have got the answer for that particular question. And we have one last question from Manish. Can we build a temperature protection module for a motor?
Yeah. I honestly didn't get this question. Yeah, we can.
Okay.
So probably, who was this?
It was from Manish.
Manish, can you get in touch with us, with more details? I just typed my email address.
Yeah, Manish, maybe you can just elaborate that particular question to Vivek. Just drop him my email, or you can also drop an email to me. I'll just drop my email address.
Yeah.
So Vivek, thanks for your time. Over to
Thank you,
Vijeta.
Yeah, so I think what we will do is we have another session that's coming up on the 10th, which is around the role of edge computing in telehealth. It's done by the IoT Forum. So I'm just going to paste the link for everybody to register for the next session. Right. So, and we look forward to seeing you next over there. Thank you, everyone. It's 5 p.m. Have a great day.
Thank you. Thanks.
Thank you.